do that. So last week, we have been talking about the switch reluctance motor. So SR motor is one of the important motor, as I mentioned the other day. And key thing is the motor will be really reliable, have fault tolerance, and also is quite simple. So in theory, if this motor had been last manufactured, then the cost will be much lower. So one thing we noticed that will be about the torque equations. So the torque equation actually are related to how we differentiate the cold energy. The cold energy is a kind of the energy stored in the switch reluctance motor. In a way, we can express them by half Li squared. But notice that the inductance actually will be a function of the rotor angle and the current. So usually we don't easily to differentiate, we can assume them to be constant. But in many cases, for instance, if we assume the inductance will be dependent from the current, but that usually will be the case if we try to design an inductor which will be sufficiently near the linear curve, linear region of the BH loop, then in this case, the inductor will be highly independent from the current. So in this case, if we differentiate it, then can see that then we do have I squared in here and dl d theta. That is equal to the slope of the SR motor. So that's to say, when we control it, then we can see that the SR motor, when it rising, that means when the rotor approach to the alignment, then the inductance will be increasing. Then we are going to have a positive torque. So that means we try to attract the rotor to go to alignment to enforce the rotation. But we can also see that when the motor trying to away from the alignment point, that means the inductance are decreasing, then you can see that the dl d theta will therefore become negative, the torque become negative. So that means the motor seems to be regenerated. That means it's not a forward rotation. So that's the thing we need to be really careful. So we do have a lot of solution because in here, the torque proportional I squared. So that is to say we can stop the current at this region. We can therefore eliminate this negative torque. So that's one simple thing we can do. But obviously, you can see that the torque is independent of the current. So that's something we need to be really careful. Because in the past, most of the current for all the other motor are proportional to the current and also proportional to the magnitudes. That means when the current is positive, the torque is positive. So, but however, because the square relationship, so that means it's independent of the current. So that's something we do need to be careful. So again, the slope is here with control about the torque. So like in here, then we can see that for the previous curve, you can see that on your sharp point here, we assume there won't be any constant inductance here. So if no constant inductance, that means when we increase here, we got positive torque, and then we quickly go to negative torque. But that's only for really ideal condition. But however, for a typical SR motor, you can see that we never can make this area and this area the same. So in this case, once we do that, that's a location we do have the good alignment. So that is to say, the inductor will not be vary at that point. So this region is happen to be equal to difference between these two angles. So that's quite realistic because usually there will be a region when we have alignment, there won't be any inductance variation. So in this case, then we do have this point have a low magnetic torque. So that's to say, when we have alignment here, so the flux can really pass through in such a way, then right at that point, there's a no magnetic torque. So you can see that the problem is if the rotor and stator stay in this particular position, even though we apply current in here, there won't be any torque generated. The motor will not have rotation. So in this case, the rotor will so-called lock up in that particular position, or maybe the rotor may not able to start. Here, the rotor, you can see that its initial position is like this. Even though energize is winding, the rotor will not start rotation. So that means we need to start from other winding. So it starts from other winding because there's no alignment here. There must be some torque. Then we can able to control the motor to rotation. So usually for this kind of the SR motor, we do it in sequence, 1, 2, 3, and so on. There must be one stator pole can energize the motor to rotate. Because as I mentioned before, the stator pole and rotor pole are not equal to each other. So that's one of the techniques we tend to do. Another thing we can see that will be about the current and the torque. So when we see that in here, when we have di, dl, d theta is equal to positive, then we do have the positive torque, the torque will be positive. But however, in that region, we need to ensure we got the current here. So we do ensure the current here. And then once in this region, we don't want any torque, we should therefore reduce the current to 0 for that particular phase. So that means for this phase, we do like that. And then once go to this region, then we need to decrease the current to 0. But of course, what I mean, the I here is total current from the input, then this I should go to other phases. So for some phase A in here, then we should have another one like the phase B in here, and then from other phase, we have phase C in here, and so on. So we use the transistors to switch the current to each of the phase in order to produce us with all the torque in each of the phase. But so that's why you can see that we don't really like this region. In this region, even though we switch the current for different phases, we still have a position, we have no torque. So that's something we don't quite like. So that means when we design this SR motor, we do need to be very careful. Firstly, we need to minimize this region, the zero inductance variation region. Or we need to make sure that when one phase is disappear, we need to quickly to move on to phase A, move on to phase B in here, and phase C in here, so that it can catch up. Make sure that there won't be any zero torque in any one of the region. So that's one of the techniques we tend to do. Right? So next, we are going to examine about the correlation between the phases and the stator poles. Xiaodong, do you think you can send a message to Xi Tao to ask him he's coming or not? Okay. To the next lecture? Since he didn't come for quite a few times, I'm a bit worried about him. Because SR motor is very important substance for power electronics, really, really important. So the number of phases and number of stator poles also has a kind of the correlation. So for the motor driver, as I'm going to show you in next few pages. So which is the motor driver? So each of the windings, say A, B, C, D, have different kind of winding. So that means this is stator A, stator B, stator C, and stator D, right? So in here, we can say that there's also equal to the number of phases. So in theory, the number of stator pole pair, one pole pair, then we equal to one phases. So that's what we trying to understand. However, the definition will be more complicated than that. Let's see for more detail about the correlation, which will be to say, so usually number of stator poles will be equal to 2mk. That's one of the typical formulation. So m is equal number of phases. So in case k equal 1, then that means the number of phases equal to the pole pair. As simple as this. So that correlation will be good for the simple SR motor 964 and X6. So for instance, 964, we got 3 stator pole pair. Stator pole pair. That means you got one of here, one in here, and one in here. For example, right? A dash, B dash, and C dash, right? So that's a pole pair. So we can say that they are equal to three phases because in here you got one winding here, one winding here. These two will connect to one set of the IGBT, right? And so on. So that means for 6-4, we have three pole pair. Then that means equal to three phases. That's what we can see. And then when we increase the stator pole pair, then that means that will become four phases. Like that. So like that. So that's to say, if we try to relate to our circuit diagram, like in here, that will equal to four phases. If we ignore this part, then that will can be for 6-4 type of the SR motor.
What if 4?
6-4. And you do remember that we say 6-4. Let's go back to that page. So like in this motor, that is 1, 2, 3, 4, 5, 6, 7, 8. So that's an 8-6 motor. This means the stator. This means the rotor. Yeah. 1, 2, 3, 4, 5, 6. So you see 1, 2, 3, 4, 5, 6 means 6 rotor poles. So the first number here means number of stator. The second number here means number of rotor poles. So that's the standard name we have been using for SR motor. All right.
The stator defines the chassis, right?
The stator number of stator pole, that means one winding here. So each we usually call them pole pair. So 4 stator poles, that means 4 pole pair, 4 phases. So that's what we're trying to say. Yeah. So that means if you're using this definition, then X6, that means 8 stator poles, then there would be 4 pole pair and 4 phases. So we use 4 sets of the transistor to drive them. That's what we're trying to understand for simple SRM. So by using this phenomenon, then we can able to examine about various combination. For instance, we got 6-4, that means one of the common one. I think you do remember what 6-4, right? We do it like in here. So that's a 6-4, 6 in the outer stator, 4 in the inner. Yeah. Then we need to use 3 phase to drive it. And that's 8-6. We got 8 outer, 6 in the inner. That's how we drive them. Do you have any problem with this? About the numbering system here, 6-4, 8-6? No problem, right? Quite simple, straightforward, right? Outer is the stator.
Here takes rotor poles.
What? Rotors. Oh, there's a typo mistake here. Oh, that's a good point. I never take notice that. Good point, yeah. Oh, yeah. I think I copied this down from some other places. And then, oh, you are good. That should be stator. That should be rotor. Yeah.
Yeah, both stator to rotor.
Yeah. So that's a typo. I will change it. Yeah. That's a good observation. Oh, how come I didn't see that? Okay. Okay. So that's a good point. You can observe that. Yeah. For instance, you say here 12 stator, 8 rotor. So there's 12 outside and 8 inside. So usually outside will be stator, inside will be rotor. But of course, there will be some exception. For instance, the in-wheel motor, do exception, you flip it inside out. Good. Then in here, you can see that those with winding must be stator, not rotating. Then the outer will be 12, inner will be 8. Right. So right in here, so that's why you can see that the number of phases are correlated to here, just related to two relationship, okay? So
It's
there,
like the stator poles are 12, but phases are 3.
which one are you talking about?
Third one.
I'm going to discuss it. I'm going to discuss the third one. So the usually will be like that. So that is to say, for this few simple motor, we're going to use this K01 combination. Yeah. And then there's a possibility that we are K equal to 2. So that all these are K equal to 1. Okay. When we use K equal to 2, that means you can see that for 12 and 8 here, it looked like divided by 2 equal to 6,4. So actually this is a 6,4 induction motor, but with double number of the pole and double number of the rotor pole and stator pole, just double that, so that we can able to have more number of the pole pair. So in this case, we are using the same kind of inverter, 3-phase inverter to drive them, but each inverter will drive 2 pole pair simultaneously. So that's why we do that. We can be able to make it more high definition. The movement will be more subtle movement to reduce the top ripple. So that's one of the arrangement too. Another concept we like to discuss with you is called the stroke angle. The stroke angle means when we energize each one of the stator, how much movement the rotor will look like. Because you can see that when alignment, when we later on we energize the next stator, then there's another movement, then another movement. So you can see there will be some step-by-step movement from the rotor. So how much is the movement for each step? That's so-called the stroke angle. So it more look like there will be one top pulse for each stroke angle. We do have, someone told me, oh, there's a formulation of this. That's how we calculate the stroke angle to be. So later on, we can see what that look like. For instance, we got 6-4 machine. So now then, during the A and A, we got alignment in here, right? So next, then he will energize B and B. So, and then of course, this will move to here. So you can see that the movement of the rotor angle will therefore equal to 360 degree over 4. So this is 90 degree minus the angle in here. This equal to 60 degree because 360 divided by 6 here. So this angle, 360 divided by 6, and this angle, okay. So actual movement will therefore equal to 90 degree minus 60 degree. So that's to say, when we excite the winding from AA to B dash, then the rotor will move from BB to next alignment. And then the actual movement will be therefore equal to 30 degree. So that's why you can see that that's our stroke angle. So you can see that for 6-4 machine, the stroke angle is 30 degree. So 30 degree is considered to be relatively large, right? Because every time when we have some electrical pulse excite on the rotor, and then you will have moved by 30 degree. So 30 degree will be usually for simple motor with less number of the stator pole pair. And then let's look into the X6 machine, how we calculate the stroke angle. Again, if we have in this alignment position, right? And then when we energize, for instance, from AA to here, once energized, then we often see that the B rotor will move to the alignment with the upper letter B. So that means the movement here will therefore look like 360 degree, which will be this 360 degree over 6, right? And then minus that's a 360 degree over 8. So this little bit angle here will be 360 degree, and this will be this one. So between A and B here will be 360 degree over 8 because we got 8 number of stator pole. And then subtract from this rotor movement here will be 360 degree divided by 6. So that's to say the movement here will be 15 degree. Okay, so that's what we can observe that. So again, you can see that x6 degree, the stroke angle will only become 15 degree. So that means by increasing one pole pair in the stator, we can therefore reduce the stroke angle by 15. That is quite good. In this case, we can able to make the ripple torque a certain improvement. So again, if we look into a higher number of the pole pair, like in here, alignment, if we energize from this to this one, from A dash to B dash, then expecting this will therefore go rotate to here. Right? So that's to say we will have this angle. This angle will equal to 360 divided by 8. And then will be subtract from this angle, 360 divided by 12. Then that equal to 15 as well. So now then, we can therefore develop a correlation for all the different type of the SR motor. Like in here, we got 30, 50, and so on. So this has some calculation for the other type of the machine too. Obviously, you can see that although we don't have a definite correlation, but general concept will be higher stroke angle, then the ripple will be worse. Then you can see that for the 4-2 machine, the stroke angle will 90, the ripple torque must be quite worse. So I think we can also look at how the 4-2 machine look like. Do we have diagram? Now, like this 4-2 machine here, the movement here, this is quite a large angle, 90 degree, right? So that means the ripple torque must be quite large for this kind of the motor. Then, so that is how we calculate the stroke angle by using this formula, right? That's a standard formula from observation. When we observe them from the geometrical joint, then we can able to work out the stroke angle. But we can also use this formula to check them. I think these two formulas are exactly the same anyway. So we can therefore try to relate them to see if they are the same formula. So we can use this formula or using our observation formula to check. So again, the effect of the stroke angle will be, firstly, we can achieve the ripple reduction. Because every time we energize each of the phase, the ripple will be reduced. In this case, we're able to improve the ripple. One of the drawbacks for SR motor will be mainly about the ripple. So that's the thing we don't quite like that. And also, you can see that even though if we do have a small stroke angle, then the top ripple will also be there. But however, that will be easier to filter by the mechanical inertia of the rotor. You can see that the top ripple will have this kind of vibration on the rotor. But if the rotor have a quite large inertia, mechanical inertia, so I don't think the rotor will vibrate in such a way because they're all filtered by the rotor inertia. So that's why if you're able to have a small stroke angle, automatically all the ripple torque can disappear. However, the control will be an issue. Why is that? You can see that when we do that, we need to control when to turn on and turn off the, so for example, in here, we need to turn on in here, turn off in this point. So we need to detect the rotor position. When the rotor approaches to this point, then we need to turn on the transistor. And at this point, turn off the transistor to eliminate the current. And then we go to other phase to turn on and turn off. So the timing control, the turn on, turn off the transistor have enough the control. We also need to control the level of the current and control all this angle. So that's why for SR motor, one of the disadvantages will be the control. The control capacity will be one issue. We need to turn on angle. So, I mean, the window are quite narrow. One thing we can see that if the motor rotates really slowly, to when we check the rotor in this particular location, we turn on the transistor, turn off the transistor is quite okay. But if the motor, as I talked about, the motor is highest speed of the motor in the world, then the speed can go up to 10,000 RPM, 5,000 RPM, 50,000 RPM. Then to detect the position and then feedback to the controller to tell the transistor to turn on will be really complicated. We need really high speed of the microprocessor. Probably we can't do that. So in the future, when you learn how to operate an SR motor, if you do a chance to go for PhD research in SR motor, they will show you how to do that. Because we do have another method to control the motor under high speed. Low speed is no problem. We have sufficient microprocessor speed to do that. But high speed, we do need to think about it carefully. So, of course, more stroke angle is preferable, but we require more number of pole. That will increase. That also become problem about copper area. You can see that, for example, like in this motor, when we have many number of the stator, then this is the copper area. In this case, that will reduce the copper area. That means less copper, more copper losses. So that's something we don't quite like that. So after we've done about the stroke angle, let's understand more about the modeling. So last week we examined about the motor torque that highly relate to the core energy. We define the core energy and then we can get the motor torque. So let's see how we understand it better. So firstly, we can start from the voltage equation for any inductive circuitry. So that's a voltage equation for inductive circuitry. The voltage equal to voltage drop on the resistor. Because all the winding have the resistive power losses plus the winding. D lambda dt is the first linkage. So when we define the first linkage, we get us the back EMF, the voltage induced from there. But however, this back EMF is different from the DC motor because the DC motor back EMF will be proportional to the speed and also the flux value. But here, then our back EMF, of course, we use first linkage, is the same story, but the first linkage here are related to the current plus the rotor angle. If related to rotor angle is quite obvious, but in a way we can also think about it can also relate to the current because when we change the current, the magnetization will also be changed. So that means when we differentiate this one, we can differentiate by the train rule. So that means one part will be di, another part will be d theta. So by using this method, we can therefore recognize there's a few correlation among each of the term. First term will be equal to the voltage drop on the resistor, winding resistor. And then second term in here, d lambda dt actually equal to the inductance because first linkage equal to Li is also equal to the inductance. And then for this one, the second term here, d theta dt is the omega. So it's something proportional to the speed. That must be the torque constant. More look like the back EMF, the EA, right? So that's to say we can therefore further reduce the equation to here, which is omega. Then we got the d lambda d theta. Then Li in here if we assume our system will have a fixed current, then we can therefore have the LD theta in here. So anyway, we eventually can get down to this equation. So that means we have three term here. Ri is the received voltage drop. This one look like LDI dt is mean the voltage due to the inductance. And then this term will build more look like due to the back EMF, three component here. So this three component will be one of the most important design criteria for our SR motor. So again, this is the inductive voltage drop, more look like an inductance. So the last one will be back EMF. So the back EMF actually are quite one of the criteria to consider maximum speed of a motor. That's similar to the DC motor. I think you all know that the DC motor equal to IARA plus EA, right? EA is equal to K phi omega. So that's for DC motor. Then for DC motor, you can see that the input voltage actually define the amount of the omega. So that means this term also define the omega 2. So that to say the whole back EMF is a key function to determine the speed of the motor. So similar to here, this is term we can determine the maximum motor speed. So the voltage define the maximum motor speed, and this omega, if we're able to read to control the DLD theta, we are able to control the speed, or we can able to have higher speed. But you can see that the dId theta and also d theta dt is more look like nonlinear. So that to say the whole motor actually are highly nonlinear motor. So let's see a very simple example to see how I understand the voltage equation. So for instance, if I got a motor running at 15 amp, then if we want to control motor at 400 hours per second, radian per second, and then the inductance profile will be 0.08 Henry per radian. And then now we control the current at 15 amp. If we control the current at 15 amp, that means rate of change of current equal to 0. So that means constant current means the ID theta equal to 0. So the resistive voltage will be 0.2. So let's see what kind of voltage will be there. Again, we use the same equation in here. This term equal to 0, because under the steady state, usually we can assume them to be 0. So now then we got 0.2 multiplied by 15 will be voltage drop on the winding. And then we also have I is 15 in here. Then we got 400 radian per second. And then we got the profile here will be this profile. So you can see that the voltage going to be 483. So for this particular position condition, the minimum voltage we need to drive the motor will be at least 483 volt. So that voltage are mainly controlled by the back EMF. So that's something we want to be really careful, right? So you can see that this kind of motor control will be not a straightforward. You can see the profile, inductance profile will be like that. So in this region, you generate high voltage here. But once in this region, this equals 0, the voltage quickly will drop. So that's why the current mode control will be really important. We need to ensure that when the current transition from this position to here, we need to ensure the current need to reduce quickly. Otherwise, this point will be too large to make the motor very difficult to operate. Of course, in this lecture, we only discuss about the motor, the machine itself. We did not talk about the control and drive. In the future, when you look at the drive, you need to be really careful about how to control the current when inductor move on from this position to this position. So let's see another tutorial how we can derive the torque equation. So we did derive the torque equation before by using the co-energy. So let's try again to see if able to work out the torque equation from the voltage equation. So again, we can start from our basic voltage equation first. So to see if able to derive the torque. But before you look into my answer, usually for this look in the torque, we can use the power. Once we got voltage equation, then we can therefore using the power to work out about the output power. And then we also know the power are equal to T omega. So basically, if we are given with the voltage equation, we can therefore use it to estimate about the torque. So that's the method we try to do. So we use another method by using this set of equation to see if we're able to provide the same torque equation as we did before last week from the co-energy. So let's do that. So the input power equal to voltage times current. So because we got this voltage, so we multiply each term by the current here. So that's why we are able to have this expression. So let's look at this term. Because you know that we have an inductance of the SR motor. So let's see the energy stored in the inductor. That will be half Li squared. Then the power for this one, we differentiate this inductance. Then when we differentiate inductance, we know that firstly, the L is not a constant. So that means we need to use the chain rule to work out the equation that is half I squared di dl d theta and then Li di d theta. That's chain rule. So that's why we can work out the equation to be that. Then in here, we have been using the L d theta, divide them into two terms because it's rotational machine. So this term will become our omega. So this term will become our inductance profile. So that's why I can change into this equation. Basically, change the power for the stored energy in the inductor, become this voltage expression. So next thing to do will be about the mechanical output power. So mechanical power must be equal to input power minus the losses minus the power in the stored energy. You see the power in the stored energy just circulate inside the inductor. The rest of energy will go to the output. So that is to say, we can use original equation from the input minus voltage drop, voltage losses due to the resistive winding, and then minus the stored energy, which we derived just now. Then we happen to be, this term we can cancel out, right? This term we can cancel out, only these two terms. And then finally, we got this term. So this term not really much familiar to us. It's the same equation as what we did for the differentiation of the co-energy. So that proves that the co-energy also related to the torque. So this is really important equation. I think you all need to memorize it all the time because that's the most fundamental equation for SR motor. Any question up to this point? So this is a standard method how we derive the equation for the torque. So next, we'd like to examine more about the magnetic flux for the motor. So usually for magnetic flux of motor, we cannot measure it properly because firstly, the magnetic flux are inside the magnetic core. We cannot insert any sensor inside magnetic core. That would disturb operation. We can't insert inside metal anyway. So that's why when we try to examine about the flux line there, we use finite element to do that. FEA. So that's a really typical software we need to use in the future if we want to learn anything about magnetic, like wireless power transfer or transformer design, or maybe motor, you do need to learn how to use the FEA software. There's a number of FEA software available. For example, like the ANSYS would be one of the typical software. You should learn how to use it. So this diagram also simulated by the ANSYS. So for instance, you can see here, when we have excitation, if we're winding in here, then we have excitation in here. So once you excite them, then you see that magnetic flux line will tend to go through in here. Of course, you close the loop as such. So that's how we do that. And then this will also tend to go through in here. So that's roughly how the flux line will go through. The main flux line will go through. But from the final element, we also observe that the flux line may not go through the outer rim. It may also go through the adjacent pole. For instance, you can see that in here. We also see some line here go through and go through here, go through the smaller loop. So there will also some small loop going through here. Although the small loop is less number of the flux line, but there will be a possibility you can go through there. So anyway, all the magnetic circuitry, including the SR motor, all the flux line will tend to go through the shortest path, the lower reluctant path. So in here, of course, that will be lower reluctant path. But because the air gap here will be much larger, it seems you don't quite like to go to adjacent poles. But when this more approach to there, you still can see some magnetic flux line go through there. So there will be a portion will go to the long alignment, a portion will go to the alignment pole pair. We also observe that all this flux line, you don't need to go through the middle. In theory, you go to the middle, but you can also go through the rim in here. So that to say, in order to save the cost, we can actually make it hollow here. Given that the flux line don't need to go through the center, because we got two adjacent lines between here, then you can able to conduct the magnetic flux line. So that's to say, if you're able to make the thing hollow, then we can able to save the cost in the center, because all the silicon ion are quite expensive. But in here, we mainly connect to the shaft. Mainly this will be the shaft, right? The shaft can be any material, can be non-magnetic. We don't need to have a low core loss material. So that means we can make the center become hollow, then we can able to reduce the costs. So you can see that the flux line transition mainly come from the stator yoke here, two of them. And then we go through the stator pole and then go through the air gap and then reach the rotor and then complete the circuitry there. So that's how the flux line being moved in the magnetic circuit. So again, because the flux line, we can see that you don't really need to pass through the center of the rotor. So it's try to go through some more direct path. You can also go through the outer circumference of the rotor. So if we're using this type of design, we can therefore using non-metal material in the center, we can also reduce the weight. We can also make the rotor become hollow, not really hollow. Hollow means we just replace it by non-magnetic material, cheaper. Using magnetic material are more expensive. So then we can do that. We can reduce the weight, reduce the cost, and improve the performance because the rotor become lighter. Lighter, they can able to improve the dynamic performance. So that's how we're trying to do. So that shows you how we design the system. So next, then we can see that how the connection of the circuitry look like in here. So these are really typical machine here. So for instance, if this will be for X6, right? This will be for X4, depending on how many transistors we tend to use here. So can you compare this configuration with the normal induction motor driver? I think for normal induction motor driver, as you can see that the arrangement between the transistor and the winding is not that. Okay. So this is a normal three-phase induction motor driver. Like that. And then we have a three-phase. In such a way, yeah. And also we got the anti-parallel diode in here. The circuit look very similar, but also quite different. So now then, can you compare with these two arrangements? This for induction motor, right? Compare this SR motor driver. Could you tell me what are the different, why they are different? Why we need to make it as such? Anybody can give me a hand, why is that? This is a very common inverter. All the inverter, AC inverter using this. But this is quite different. Although they look similar, but quite different. You can see that the winding here are put in this star connection, right? Or can be delta. But in here, we put in the winding between the two IGBT. What was the point to do that? Why can't we put it in such a way?
We saw when it get aligned, the torque become 0, right?
Mm-hmm.
And we have to move keep moving to energize others poles. That's why.
Yes. You see the winding here, A, B, C, D, each winding here, they are highly independent from each other. So when you energize A, we usually turn off B, C, and D, and so on. Because as I mentioned before, we only energize one set of the stator winding to move the rotor. So we don't need to energize a few of them because when we arrange X6 or 6-4, only one set of the stator pole can have alignment. All the other set will not have alignment. So we only energize one of them. So that means to do that, in order to energize A, we must turn off B, C, and D. How to turn off it exactly? We must using two transistors. Make sure these two transistors will turn off B. These two transistors will turn off C, and so on. If we have any common sharing for the IGBT with other phases, we cannot ensure it turn off. Okay? So that's why we do it as such. But here is different. For this kind of the motor system, when we energize them, then the current will go to here, probably you return to here, or maybe you can also return to here. Because they're three phase, each of the time the 120 degrees phase angle, they do have some voltage there. We're not turning off any one phase. For induction motor drive, we always three phase are being turned on, but in different voltage, different phase angle. But in SR motor, it's different. We only turn off one phase. So that makes it different. So now then.
So this means it is efficient?
Really good. All the motor drive 99% efficient, not 99, 97. 97, 98, depend on which one, who is going to design it. Yeah, really good. They're similar efficiency anyway. They are all the same. Each winding will have to use two transistors and two diodes. So next question I'd like to ask you will be, do you see the diode D1 and D2? Do you see that they are different from this? The diode is anti-parallel. So for conventional diagram here, we call this one anti-parallel, right? But in here, they're not independent. They connect in such a way. Do you think this is wrong drawing? What happened to the dial? Anybody can give me a hand why it is?
It's not integrated, right? It is, because here we are not stopping. Here we need continuation of the.
Yes, very similar. I think your answer. I know you understand it. I'd like to hear the other person here. What do you think? I mean, what do you think? Why the dial arranged in such a way?
Because whenever that phase is turned on, we want the current to keep running in a loop and not let any diode cut out the current. So we just keep running.
I think you know the answer, but it's just using the orientation, not quite enough. Xiaodong, what do you think?
I think why in SRM using the DC?
Yeah, all the inverter, we can also call it inverter anyway. They're all using DC, right? DC to AC.
In the diode is for independent from the other.
In mind, the diode will be connected separately, not independent with RGB. If you do a star connection with winding and RGB,
If connected by anti-parallel, if we drive the B windings, the A also we energize.
Let me hear the answer. The signal, what do you think?
So for purpose, use this diet, I think is for reduce the content. So one don't use the anti-value. Maybe use this way. We can tolerate the doses from up to the down and current is some. And yeah, maybe it can make the release speed double.
With the release, with the lock.
So when the transistor turn off, that means the inductor will create a BMF voltage, the reverse voltage, and pass the maybe not.
Maybe that's the first time you see this kind of circuitry in the past. Usually, everybody will use this circuitry for the inverter. So the difference for this will be like that. As you see from previous few slides, we talking about the current. So we need to turn off here. We turn on here, right? Once it's turned off, you can see that we got high current stored in the inductor. So this energy half Li square cannot disappear instantly. So that's to say for all the inductive circuitry, we cannot turn off the inductor instantly. So what we need to do, if the current flow in here, even though turn off these two, we still need to allow this current to continue to flow. So that means this current will flow through here, return here. Okay? So that's more look like power regeneration. So that is to say we need to reduce the current when we turn on, usually in this path, right? Turn on in this path. Turn off, the S1, S2 is not going to conduct. then you therefore go through the D1 and D2. D1 and D2 is connected to this terminal, connect to the plus and minus. You really quickly can reduce the current to 0. So that's what we need to do. If you're using this one, impossible. The winding in here, how are we going to reduce it? You can see that if we're putting the transistor in here, of course, we can use this one. Yeah. VDC. When I turn on, these two will turn on. When I turn off, even though this turn off these two, this current cannot go through the diode. Cannot go through the diode, impossible. They will create a large spark. High dIdt, dIdt. This is equal to, say, 1 nanosecond. Then the voltage induced will be 10K, 100 kV. They will burn all the transistor. So we need to do it as such. So that's a special arrangement for SR motor driver. So do remember that. That's one of the drive circuit technique we are using for this kind of the switch reluctance motor. So that's why you can see that when you energize this motor, as you can see that from the diagram we have here. So for this thing, turn on here, the current will be like that. So when turn off, we need quickly reduce the current to 0. So this, we still have some so-called tail current here. We don't like this current because this current will create the negative torque, right? The torque is positive, that will create some negative torque here. So this current need to be reduced really quickly. So that's why you can see that in here, we will therefore return to the source using the input voltage, high voltage, to decrease the current. You see some of the circuitry, they may using other method to reduce the current really quickly. For instance,
By inserting resistor by load.
yeah, they insert additional voltage. So in theory, they have this transistor. See here? And then they will go to this one in all the high voltage to reduce the current, because for good design, we need to reduce the current ASAP as quick as possible. So that's many design in here. So you can go through a lot of the literature to understand more about SR motor. The circuit design and method are so many. You can also see that this kind of the motor driver who do have a problem. This inverter is really common, low cost, because industrial motor has been in the market for more than 100 years. So that's why really low cost. All the inverter bridge, we call it inverter bridge or inverter modules, are really low cost. We call it inverter modules. Are really low cost. You can go to any shop like DHK to buy it really low cost, really common available. But this one is not available. When you buy this one, they already solder these two together. You cannot split them into two halves. Even though you can, but you cannot split the dial into two halves. You see, when you see this package, the dial already embedded inside the package. So I do have another lecture to show people how to use the IGBT package. So the IGBT and the dial already embedded inside the substrate. You can't divide them. So that's why you cannot using this kind of the motor driver for this purpose. So you need to make it deliberately by yourself, or maybe you need to use a number of this one to construct the SR motor driver. That also causes a lot of problem. For instance, you cannot buy this one. You can only use individual component, discrete component, using, like in here, 8 IGBT and 8 diode to do your own soldering to construct your own SR motor driver. So that's really much inconvenient. Or can you use this driver to connect to this motor? think about that. If you only given with this kind of the inverter, how are you going to do that?
We will,
Just one of the question in the quiz next week. Yeah. Now, this is not available in any market. But now you only provided with this, as many of this one you like. You can give you 3 phases, 4 phases, or a few of this. How are you going to use this one to drive a motor? Do you know how to sketch the diagram? Circuit diagram?
I think we'll connect the diode in a way that we can.
Use a paper. Or you can try it on our whiteboard. How are we going to do that? Think about that. This method is quite standard. In the old day, when I started to work on SR motor, that was about 30 years ago. I think more than 30 years ago. And during that time, SR motor is still not yet mature. And then we need to use different methods to drive the motor. We can use discrete component, but sometimes they're not reliable. And then I use the power module like this 3-phase module. Then we need to use a few of this one in order to connect with this SR motor. So the question is how I can use this. This is available in the market. How are we going to use this one to drive this 4-phase or 3-phase motor? Can you sketch it to see, are you able to do that?
Do we have time?
No, we just a few minutes, no problem. We still have time. How to sketch it, and then we go for the answer. Use a paper or using your iPad to see able to sketch it. Of course, when you back home, then you can press the button in the internet, you can get the answer. But it's very well known. But I like you to think to see can you do that? That is to test you how good you understand the concept for SR motor, how you're going to use existing available component to drive an SR motor. Okay, think about that. I can give you an answer up after 2 minutes. Done that?
We can give you the concept.
After then, they show to me to see how your research skill, maybe to examine your research skills.
My thinking is because what we can do is, no, I'm just giving concept. We will connect this in a way. Because here it is interpreter, we will try to make it this diode. So we think
This
can connect.
is the power module you can get from market easily, because that's the one which going to construct the industrial motor driver. So we have only provide this kind of the modules, how you present that.
So we can connect this in a way that the output of this with the input of this, just and then connect with this. That's why what we have there.
Sketch it in detail so that you can understand what we do. Are you able to sketch it?
Yeah, I will use the Wi-Fi.
Okay. In a second, let's see if everyone has done that, then we can start to use the board. Good. Are you okay with that? Yeah, that's the way. Maybe you can go outside to see if we're able to do. do that, sketch it.
I just want to try this. I don't know.
No harm to try. I mean,
I have no plans. So I just think about.
okay. Just imagine now we are not going to connect to a industrial motor.
Yeah. So
And now this is available nowadays. This is how the three-phase power module is now available. How are we going to connect it?
we want to give one. You cannot can.
I can see that a few of you have done that, yeah.
Right? It is this way. And here, and they can, if we open.
Then in this case, you are overlapping some winding. The key thing here, we need to have independent control for each of winding because they need to be independent in order to
Yeah.
provide the fault tolerance.
Oh,
Each winding need to have no connection with other winding.
so this is has interaction.
Okay, that's okay then. Yeah. Okay. So the answer here will be, you see, to do this one, of course, a few of you have done that. We just need to connect the inductor across here. So we use two, that's called one inverter leg, two inverter leg for one phase. So because when I turn on, it go through in here. When I turn off, you see this current. When I turn off, this current will therefore flip through here, flip through here. Do that. So that means we are actually using conventional power module. We need to double the inverter leg to do the same kind of the job. So two inverter leg put in here. So you can see that this lever will be used, right? And this dial will never to be used. We're raising the component, but we can still use the conventional power modules. Just connect the winding between the two midpoint of the inverter link.
So when it is turned on, so can you?
So when you're on, when turn on, so the current will go through in here, right?
Yes.
That's okay. When it turn off, then this current need to go through this dial. Go through this dial. Okay. In order to complete the turn off. Okay, that's all. This is a standard method we use. Of course, in the research or in many other literature, we do have many different kinds of arrangement to arrange the circuitry development. So that's it for today. We'll continue that.